Okay, so now we're ready for the geometric series. So minimize the camera and let me give you a quick example for geometric series. Okay, so if I want to look at a geometric series, let's use this one, 6, 12, 24, 48, and 96. So just as a quick review, we can't keep adding the same number. We could add 6 to get 12, but if we add 6 again, we won't get 24. So what are we doing? We keep multiplying, and I'm using the easy example of just doubling the number every time. So we could just keep on going, okay? So that's an example of doubling. Let's just make sure we understand the notation. So if I said, what is a of 3? It's simply the third term in the sequence, which is 24. But this would get a little trickier. If I said, what is a of 20? We would have to we could keep writing out terms, but that is going to get a little tricky. So we don't want to have to write it out. So we want a formula for that. So when I have a geometric series, we have some starting value a, but then we keep multiplying it by a number called the common ratio. And we're going to do that n minus 1 times. So let me just highlight a few things. So r is the common ratio. In this problem, we keep multiplying by 2. So 2 is the common ratio. Once again, the n minus 1 comes in because we don't need to multiply by r to get the first term, but to get the second term, we'll multiply by r once. When n is 3, that's the third term, we'll have multiplied by the common ratio twice, and so on. So if I want to find a20, I will simply take the first term, which is 6, and I will multiply by the common ratio, which is 2, and I will do that 20 minus 1 times, or 19 times. So this is 6 times 2 to the 19th power. That's a good problem for your calculator. So I'm just going to pause quickly and there you have it. The number is 3,145,728. So that brings up the power of doubling. By the time we have doubled 6 20 times, I'm sorry, 19 times, we'll be up to a very, very large number. So while 6 doesn't seem big and 12 doesn't seem that large, if we keep on doubling, this thing exponentially grows. So you can see actually the general formula for the nth term is actually an exponential growth formula. You have some starting value a, and then you have a base. The common ratio r is just like the base, and it's going to grow once per unit change in n. So that is an exponential growth, and that can get very large very quickly. So that is what a20 would be. Now we could use the same sequence, and we could try to find out some partial sums. So let me just write the sequence over again: 6, 12, 14, 28, and so on. If I had asked you what is S3, that would be 6 plus 12 plus 14. That looks like 32. So that's easy to compute without a calculator or without any special formulas. But if I had said, what is S of 20? Finding a of 20 was hard enough because it's such a large number, but adding all the numbers from the first term up to that 20th term would be quite a feat. So we probably want to have some formula that will allow us to do this. So let's recall that there was a trick. If I wanted to find S of n, let me just write it out this way. There was a trick. I could take r times S of n, and that would end up being, if I leave a little space, we would have a times r plus a times r squared plus all the way out to a times r to the n minus 1 plus a times r to the nth power. And S of n was going to give me a plus a times r plus a times r squared plus dot, dot, dot. But it was going to end at a times r to the n minus 1 power. And remember what our trick was? It was to take the difference between these two things. And when we did that, we ended up with r times S of n minus S of n was equal to, everything ends up canceling out when you do the subtraction except for the first and the last terms. So since the first line is what's being added, you get a times r to the n minus a, and with a little bit of factoring, we can see that this is S of n times r minus 1 is equal to a times r to the n minus 1. So what is the sum? The partial sum will end up being a times r to the n minus 1 over r minus 1. And I like this version of it if r is bigger than 1. Okay, so let me write nice when r is greater than 1. Okay, but there's another version that's not in the book that I like to write if r is less than 1. So I just rewrite it as 1 minus r of n, so that's the negative of the numerator, over 1 minus r, so it's the negative of the denominator, and the double negatives means that it's equivalent. So this is nice when r is less than 1. Okay, so you can use either version of it, whatever one is most useful for finding a partial sum. So we were supposed to find S of 20. So if I need to find S of 20, I need to put in A, which is the first term. That was, I believe, 5. Let me see. Oh, nope, I'm sorry. A was 6. That was a previous example where A was 5. So if we look at the problem, go back down here. The first term, whoops. The first term was 6, all right? And we're going to be looking for the 20th partial sum. And we have a common ratio, R of 2. So let's go ahead and fill this in. So we know that the first term is 6. We're going to use the top formula since R is bigger than 1. So we'll have 2 to the 20th power minus 1 all over 2 minus 1. That's nice that the denominator just happens to be 1. And let me just pause and enter that in my calculator. All right, and the answer is a walloping 6,291,450. Now, if you're paying close attention, okay, this is very close. If you notice, let me go back to our answer for what was A20. Okay, so if I look at what our answer for A20 was, it was 3 million and something. Okay, so the answer we just got was pretty much a doubling of A20, which means it's almost A21. Now the reason it almost comes out that way is because this minus 1 in here doesn't matter that much when you have 2 to the 20th. We really, the total sum is almost equal to the next term. Now let's take another example and work with one that's getting smaller and smaller and smaller. So here's another example. Let's start with numbers like 9 and go to 3 and then 1 and then 1/3 and 1/9 and so on forever. Okay. Now it'll be pretty easy to figure out what S3 is. That's just 9 plus 3 plus 1, which is 13. So it would be easy to find partial sums for the low values of n. It would be a little bit trickier if I wanted to find S of 10, right? I would probably want to turn around and use the formula A times, it would be, I'd like, since R is, well, let me step back for one moment and define what everything is. Okay, so I would want to work with the formula, and I would note that A, oops, A is 9. Looks like we have a common ratio of 1/3, right? So if I wanted to find a term that was later on, I could use my S of n formula. S of n is equal to, since the ratio is smaller than 1, I'm going to use 1 minus r to the n all over 1 minus r. Okay, so if I wanted to find S of 10, I would say, the first term is 9, and I would take 1 minus 1/3 to the 10th power all over 1 minus 1/3, right? So the denominator will come out to be 2/3, but this is going to get a little bit messy, so we might as well just get our calculator out and get a value. And so let me pause the video. So you can see we have a value for this of 13.4998. I'm copying all those digits for a reason, because we're going to see that we're actually approaching a number even if even if we add many, many, many terms. Okay, so let's consider what happens if S gets much larger. Okay, so let's consider, I'm sorry, not if S gets much larger, if N gets much larger. What would happen as N approaches infinity? So once again, we had derived this formula before in class. And I think we had convinced ourselves that if R is less than 1, so in this case it's 1/3 to the N, as N approaches infinity, right? Let me actually make a little space in here and use formal math notation. So we'll be seeing more of this later in the year, but in the limit that N approaches infinity, if you just in your calculator use 1/3 and then you keep multiplying by 1/3, or if you wish, you can just do 0.3 and keep multiplying it by 0.3, you see that it actually gets closer and closer and closer to 0. So while it never reaches 0, its limit actually is 0. So what we can do in the formula, if N is approaching infinity, we can say that the sum, we'll just cross out the N, is that part is going to go to 0. And so the partial sum can just be rewritten in the limit that N goes to infinity. S of N is going to be equal to A over 1 minus R. So how does that apply to this case? Let's look at what happens. S of N, okay, so in the limit that N goes to infinity, that means we would just keep adding terms forever. We would start with our A value, which was 9. And then we're going to take 1 minus 1/3. So that's 9 over 2/3, which is 27 halves. Okay, now if you write that as a decimal, that is 13.5. Now it would be useful, compare that to the last answer. So notice by the time we added 10 terms, we were very, very, very close to 13.5. In fact, it would have been easy to round it to 13.5. So if I add an infinite number of terms onto that, because the terms are getting smaller and smaller, it really doesn't make the entire sum grow by much at all. So that's what happens when we have a geometric series with an infinite number of terms. As long as the common ratio is less than 1, you actually can get a total answer. So it's kind of intriguing that you could add an infinite number of terms and end up with a finite answer.